Right, we'll go ahead and get started. Welcome everybody to Wednesday Compass Seminar. Today we have James Hlywiak, and he will be presenting about tropical cyclones. James is a fifth-year PhD student with Dr. Dave Nolan, and he's studying boundary layer surface interactions with tropical cyclones near land. He obtained a BS in meteorology from the Pennsylvania State University, with minors in mathematics and marine sciences. He's got 2 peer-reviewed papers in Journal of Physical Oceanography and Journal of Physical Chemistry A. He's attended both international and local conferences. He's done some review work for GRL, Journal of Atmospheric Sciences and Ocean Sciences. He has done some hurricane discussions, map discussions with the Hurricane Research Division. And he was a University of Miami fellow during his first 2 years here at the Rosenstiel School. Today, he's going to be talking about tropical cyclone wind field decay and the evolution of the boundary layer structure during and after landfall. All right, James, there you go.
All right, thank you very much, Anne. Good afternoon, everybody. Let me share my screen here. Let's see. Okay, so does everyone see my PowerPoint screen? I will take that as a yes.
Yes, we do.
Okay, great, perfect. All right, so as my title suggests, I'll be talking about the inland decay of the tropical cyclone wind field before, during, and after landfall, as well as the structure of the boundary layer and how different land types affect the structure and the total wind speed at the near surface. All right, for anyone interested, this is a severe tropical cyclone Abigail, which made landfall in northern Australia and managed to remain as a pretty strong storm pretty far inland. So surface interactions are going to be a key aspect of today's talk. Okay, so I'll start off with a little bit of a motivation and background. In part 2, I'll be talking about what will be the second results chapter of my dissertation, the inland TC wind field decay. In the third part, I'll talk about the boundary layer modification, and then I'll finish up with some future work and goals that I hope to accomplish by the end of my PhD sometime next year. And just a few key terms that I'm going to be throwing around a lot today. I want to highlight TC, it just means tropical cyclone. It's the same thing as a hurricane here, so I'm going to be using the 2 terms interchangeably. And also Z0 for the surface roughness length and SC for the volumetric soil moisture content. I'll be using those 2 terms pretty frequently, and the abbreviation Z0 and SC. So start off with a little motivation. So on the left here is a figure from Klotzbach et al. 2017. Showing that damages due to landfalling hurricanes are only increasing significantly over the past decade or over the past century as more and more people move to coastal regions and within the coastal regions. So definitely a huge problem for society and for capital and for businesses and basically anyone who lives near the coastline. But also lots of damages can still occur pretty far inland. Here are 3 recent hurricanes that have made landfall over the continental US and have caused billions of dollars in damages pretty far inland. So a huge problem. There's still a lot of uncertainty in how hurricanes decay. And so a lot of work is being poured into understanding the inland decay. So just to make sure we're all on the same page with why surface interactions are so important, I'm going to spend a little bit of time talking about TC energetics. So this figure here on the right is a depiction of the classic Carnot, the theory of a hurricane as a Carnot engine. You have an inflowing branch, A to B. This is an isothermal expansion process where the inflow collects energy from the surface. And then from B to C, water vapor is condensed out as latent heating, and this latent heat is converted into mechanical energy, which the storm uses to do work. The loop closes with adiabatic contraction and a theoretical subsidence back to point A. You can represent this process using an entropy temperature diagram here on the bottom. And the more energy the inflow, this A to B leg, is able to collect from the surface, kind of the larger this volume of the box down here is. So if the storm was over the ocean and the ocean were to cool a little bit, we would see this leg get truncated, leading to less overall work because the area of this box, the integral of this box, is proportional to the potential work that the storm is able to do. So surface momentum and enthalpy fluxes can be represented by the bulk aerodynamic formula. Here's momentum on the top. Momentum is negative because the storm imparts or loses momentum to the surface. It's a function of the square of the wind speed, but also of this drag coefficient here. And this drag coefficient increases for more frictionless surfaces. Here's the equation for enthalpy, which is a function of CK, which is the coefficient of enthalpy exchange, but also of the saturation entropy or saturation enthalpy difference. So the warmer the ocean and the cooler the surface above it, kind of the more heat exchange occurs from the surface into the cyclone. So over warm ocean waters, this works pretty well, and the TC acquires energy and friction is low. However, once a storm approaches land, friction increases, which increases the amount of momentum the storm loses, and the low surface enthalpy of inland surfaces. These two effects in combination lead to a fairly quick decay in most cases. So that leads us into part 2, where I'll be talking about work from a recent paper that Dr. Nolan and I submitted, in which we tested the sensitivity of land-falling tropical cyclones to different land types. Those land types varied through the inland surface roughness length and the inland soil and moisture content. This manuscript is in review. So soil moisture is pretty easy to understand conceptually. It's basically just the saturation or the fraction of the model grid cell that is occupied by water instead of soil. Roughness length is a little bit harder to conceptualize because it's not a physical length, but rather a length scale that depends on characteristics of objects at the surface. Generally, a very general rule of thumb is that this Z naught is approximately 10% the height of whatever object you're referring to. But this isn't always the case, and Z naught tends to be very heterogeneous over a large region. So here's a table showing some common Z naught values for common land types. Over the ocean, Z naught is pretty small. But then once you get into more tall grass regions and agricultural regions, forested regions, heavily suburban and urbanized regions, that Z naught value can rise from a few centimeters all the way up to a couple meters. The drag and enthalpy coefficients that I talked about a couple slides ago are both a function of Z naught. So Z naught really plays a huge role in characterizing the turbulent fluxes between the surface and the atmosphere. They're both proportional to Z naught. CD is directly proportional to Z naught, meaning as you increase the roughness, this drag coefficient is going to increase. The CK is also proportional to the square root of CD. So as you increase Z naught, you're also increasing the efficiency of the flux transfer of heat and moisture. However, to a smaller degree per increase in Z naught than you would increase the drag coefficient. So there's some cancellation between the two effects, but for the most part, increasing Z naught is more harmful for a hurricane. Here's an example of some vegetation types across the continental US, compiled by the USGS. I'm going to highlight some regions around the Gulf Coast and the eastern coast where hurricane landfalls are common. So along the southeast United States is a pretty heavily forested region with a few exceptions here and there. It has a relatively high Z naught of about 80 centimeters. The New England region is pretty similar to about 86 centimeters. And this is an important time to mention that the roughness length does not account for terrain, such as mountains. So the Appalachian Mountains are up here, but Z naught really only accounts for whatever obstacles are on land. And then a third region I want to highlight here is in southern Louisiana and eastern Texas. This region features a pretty low surface roughness value because this area is very swampy and pretty smooth because a lot of it is water. So empirical inland decay models have been around for a few decades and are incredibly helpful in predicting and forecasting the inland decay of storms. It really all started with this Kaplan and DiMaria 95 model. This empirically derived statistical model was taken or was computed or empirically fit observations of the inland wind speeds for decades of storms. These papers, 1995 and the subsequent iterations, found that intensity at landfall, the translation speed at landfall, and the distance inland can explain 93% of the Atlantic variance in inland intensity. And by intensity, here they mean the maximum wind speed at one point. Vickery et al. In 2005 similarly found that the decay rate is inversely proportional to the RMW. So the smaller the RMW initially, the faster the decay rate. Other empirical functions have been fit by other studies across the globe. Wong et al. In 2007 found that low-level moisture is important to determine the decay over the South China Sea region. And then Kishwal et al. In 2013 found that the time spent and the fraction of the TC over land in the East Indian Ocean are important for determining the inland decay because the coastal geography in that region is just so complex. So even including that last one, there is a pretty wide, noticeable lack of inclusion of surface properties such as roughness, length, soil moisture. Subsequent iterations of this 95 model took a look at different regions and fitted unique functions for each regions. I think 2001 focused on the Florida Peninsula, and 2006 focused on the New England region. However, the fact that these functions vary so much that the coefficients have to change per basin indicates that there is a strong sensitivity of the decay to different surface properties. And so while these works are hugely influential and have done a lot of good and are very successful, there's still lack of understanding of the physical mechanisms and sensitivities for static fixed surface properties and inland TC decay. So these are some studies that have taken a look at how the soil thermal properties affect an inland cyclone. So this chart's taken from Tulea 1994, this first paper here. And he showed that when you increase the thermal property of soil, so that includes not only the moisture, but the heat capacity and the thermal diffusivity of the soil, he found that when you increase that, the properties well beyond that of soil, closer to what's typical over the ocean, hurricanes can be sustained over rougher terrains, essentially. And these other papers found very similar results. And we know from observations that storms can intensify and remain strong inland, such as Tropical Storm Erin, which in 2007 actually reached its peak intensity when it passed over Oklahoma, of all places. So the months preceding Erin's passage, Oklahoma experienced heavy rainfall, which saturated and warmed the soils there, creating a quasi-ocean-like environment, or what's called a brown ocean. However, Erin was still just a weak tropical storm, so there's a lot of uncertainty whether soil moisture in particular can play a big role in modulating the decay of a strong or a major hurricane making landfall. Okay, so now getting to my results. As I mentioned, we ran idealized simulations using a pretty recent version of the weather research and forecasting model. And when I say idealized here, I just mean that the data comes from representative soundings that are pretty similar to typical like atmospheric soundings and ocean conditions over the tropics that hurricanes regularly encounter. So this data doesn't come from a single case observation. I used 4 domains here, with the innermost domain being a vortex following a domain featuring a resolution of 1 kilometer. It's 480 by 480 kilometers over the center. I started off with 1 ocean-only run with no land. And this track here, this horizontal-ish line here, represents the track of that ocean case. It was initialized in the eastern part of the domain, and I allowed it to move westward with an easterly steering flow over the course of 8 days. Over this time, it reached approximately Category 5 status. After about 3 days of running that, I paused it and reran it 9 more times with 9 different land masses initialized in the western part of the domain. So this big green square, or rectangle here, represents kind of what my land mass looked like. A very simple coast, featuring no bathymetry too, I should mention that. So then I restarted with these 9 different land cases. And in each case, landfall occurred about 60 hours after restarting, resulting in a pretty consistent translation speed of 5.5 meters per second. Now, I mentioned earlier that that those other studies have found strong sensitivity of the inland decay to translation speed. However, this is a pretty typical translation speed for storms making landfall in the Atlantic, and trying to test every combination of translation speed would just be insane and just way too costly from a computational standpoint. So we only tested this one translation speed. We also neglected the diurnal solar radiation cycle, because this radiation cycle has a huge impact on land and could contaminate our results effectively. So to represent fluxes over the land surface, I used the NOAA land surface model, or NOAA LSM. Ground temperature is calculated from this prognostic equation here, which is a function of C, the heat capacity, and KT, the thermal diffusivity. Both of these are in turn functions of the soil moisture itself, SC. So increasing soil moisture increases C as well as KT. And here's an equation for the thermal inertia, which I mentioned a little bit earlier. It's the square root of the product of those two. Thermal inertia is just a very nice way to compare different thermal properties across different regions, all wrapped up in one nice number. So on the left here, this is a table taken from my paper. These are the 3 soil moisture values that I used for my simulations, ranging from 0.05 or 5% all the way up to 0.6 or 60%. And the representative or the respective thermal inertia values are down here in this last column. I've also listed some thermal inertia values from other studies, from 2 of the studies that I listed a couple slides ago, the Tulea 94 and Emanuel et al. 2008. And so you can see that my range of thermal inertia values represents a broad but realistic range. And that's really important, because we wanted to test realistic surface types. We know that turning land into ocean helps a storm to survive for a long time inland, but the question here is, can a realistically saturated soil slow decay significantly? So in this table, here's a matrix of the 9 simulations, the 9 landfalling simulations that I ran, with soil moisture on the left and roughness length on top, 3 of each, resulting in 9 simulations. So each simulation featured 1 Z0 value and 1 SC value. And I named them based on the surface attributes. So the smooth case with the saturated soil resulted in the smooth and wet simulation. Conversely, the rough simulation with the dry soil resulted in the RD simulation. Both of these are constant and homogeneous in time and space. So now here are plots of intensity, just basic intensity metrics. S10 max being the maximum total wind speed at 10 meters for a single point. This is minimum pressure in the middle, and integrated kinetic energy on the bottom, which is essentially just a measure of the total kinetic energy output by the 10-meter winds. So on the left, I've averaged among my different Z0 cases. that would be averaged down the column vertically of this matrix on the bottom. On the right, I've averaged across the soil moisture cases. So that's wet, moderate, and dry, smooth, moderate, and rough. And immediately we can see that the storms did make landfall as very powerful, high in category 3, low in category 4 storms. And immediately you notice that all storms decayed pretty rapidly. So none of these land surfaces was particularly favorable for a landfalling major hurricane. Within about 12 hours or so, each one of these decayed to about a tropical storm intensity or low end category 1 intensity. However, we see that there's a much greater sensitivity to the roughness length and a smaller sensitivity to the soil moisture. So the smooth cases by each metric here are stronger than the moderate and the rough cases when looking at roughness alone. When looking at moisture, I actually see a less clear relationship between moisture and inland strength, as the wet cases, as all cases are relatively the same intensity within 12 hours of landfall, which increases. We see that the wet case is marginally stronger inland as time progresses and as the storms weaken. So the wind-based metrics, IKE and S10 max, are 40% for the smooth case to 60% for the rough case, weaker by 12 hours. And the minimum pressure remains a little bit stronger inland. It kind of lags the decay of the wind-based metrics, featuring percentages of 35 to 55% by 12 hours. And this indicates that the upper level vortex, for which PMIN better represents, remains stronger inland, or at least decays slower than the surface-based metrics, or the surface-based wind metrics, I should say. And in fact, these plots are essentially the same as before, except now I'm plotting the maximum azimuthally averaged tangential wind speed at 10 meters along the top, the maximum azimuthally averaged tangential wind speed at 2 kilometers in the middle, representing the circulation above the boundary layer, or the circulation that isn't immediately affected by the rougher land surface. And the bottom here, I've shown the reduction factor. So that's just the ratio of the 10-meter winds to the 2-kilometer winds. Again, for Z0 on the left and soil moisture on the right. So you can see just by eyeballing the charts, you can see that the 10-meter circulation decays faster than the 2-kilometer winds, indicating that the weakening takes a kind of bottom-up approach. And consequently, you can see a pretty large sensitivity for increasing Z0 as or in terms of reduction factor. So that's just the winds are more similar in the vertical direction for the smoother cases, but there's a larger difference between the winds at the top of the boundary layer and the bottom of the boundary layer for the rougher cases. And again, there's very little sensitivity to soil moisture, so I won't spend too much time on that. So now I'm going to talk about more size-based metrics to evaluate the total wind field. So in this plot, here are the averaged ensemble members for the roughness length cases, and the average ensemble members for the soil moisture cases. In the dashed lines, I have the azimuthally averaged radius of tropical storm force winds. In the solid lines, the radius of maximum winds, also azimuthally averaged. So again, if you take away anything from the talk today, just know that there's a greater sensitivity to these realistic Z0 values than for most of these fields and variables than for the soil moisture cases. However, an interesting reversal in the trends of the radius maximum wind expansion and the TSR contraction, tropical storm force radius contraction, occurs where we see initially within 20 hours, we see kind of a slower rate of expansion of the radius of maximum winds within the dry cases. After 20 hours, the expansion of the dry cases, the RMW expansion, increases more so than the wet and the moderate cases. So this is going to come up later on in a few slides, where I explain kind of why this sensitivity to soil roughness takes a while to become apparent. Okay, so here's a plot of the maximum 10-meter surface wind footprint. So this is just the maximum winds for each point, each model grid point covered by the innermost domain throughout the course of this simulation. The plots here match up with my different simulations down here. And storms are moving from the right to the left in each plot. Track is shown in this by the plot running perpendicular to the land, which is this vertical black line. The innermost contour is the hurricane force wind contour, and the outer contour is the tropical storm force wind area. So again, we see a strong sensitivity from Z0 going left to right. However, increasing the SC expands the far wind field. So we see more occurrences of tropical storm force winds in the far field, and especially to the right of motion. And this is because it's not only due, this right of motion asymmetry isn't only due to the motion-induced, the storm motion-induced asymmetry, but also due to the fact that within a few hours over landfall, take the MW case, for example, part of the circulation, or the part of the circulation to the right of the storm originates from over the ocean. So it's advecting warm ocean water, air, over on the onshore side of the storm, whereas the winds on the left side of the storm originate from over the ocean, or from over land, excuse me, and spend a longer time over land. So this just further degrades and decays the wind field on the offshore side. So now I wanted to quantify the radial decay by quadrant. So I modified the Kaplan and DiMaria 95 inland decay model. That model mainly only accounts for the intensity of the wind. And what I did was I azimuthally averaged along each storm relative quadrant for each storm and computed the radial decay as a function of radius. So that function is here. The important part of this function here is this alpha. So alpha is the e-folding decay rate. And I've plotted alpha for the Z0 cases here and for the SC cases here. So larger alpha means a faster decay rate, essentially. So we see that the radius of maximum winds, the strongest winds decay the fastest. And at least for Z0, these inner core winds, and to an extent, the outer core winds, are pretty sensitive to Z0. So decay increases for increasing roughness, decreases for the smooth case. The relationship for SC is a little bit more complicated. So we see that the moderate case actually features the highest decay rate, which is kind of weird. The smooth case features kind of the lowest decay rate. And the decay rate really manifests itself, or the sensitivity really manifests itself within the outer core, and especially to the left of the storm. There's really not much of a difference at the initial radius of maximum winds. There's a little bit, but especially not as much on the right side. Really the sensitivity lies in the outer core. Again, the front and the right quadrants decay faster just because they're coming from they're starting out at a stronger speed. And interestingly enough, the wind actually increases within small radii, within the initial radius of maximum winds. And this is just because as the storm is making landfall, that high momentum air is being diffused inside of the radius of maximum winds due to that discontinuity in roughness length. So I wanted to understand why we saw such a little sensitivity to soil moisture. I expected maybe the wet cases would be similar to, or produce a brown ocean effect and favor a slower decay rate. However, we see that the sensitivity within 12 hours was pretty small. So here I've plotted latent heat, surface latent heat fluxes on the left, and sensible heat fluxes on the right for the moderate wet case, the moderate case, and the moderate dry case going top to bottom. These are fluxes taken at 2 times. These are snapshots at 3 hours inland and 30 hours inland. And positive just means from the ground towards the atmosphere, negative, vice versa. So we see just looking at it shortly after landfall, there's a much more latent heating occurring, or a much higher transport of latent heating occurring for the wet case. There's almost no latent heating associated with the dry case. Conversely, though, there's an equally as strong negative flux of sensible heating for the wet case, as the additional moisture, or sorry, as the storm evaporates the additional moisture, which cools the surface, leading to an enhanced downward sensible heat flux. So over the ocean, latent heating typically dominates sensible heating by an order of magnitude sometimes, or by a lot all the time, sometimes by as much as an order of magnitude. Here though, over land, the two are of comparable magnitudes and effectively cancel each other out. Overall, for these simulations, we do see a small net gain in enthalpy for the wet cases. And this is going to help explain why the sensitivity to SC increases in time. So here, to explain the timing of that increase in that heightened sensitivity, I've plotted the 2 to 6 kilometers azimuthally averaged, vertically averaged diabatic heating rates within the moderate wet, moderate, and moderate dry cases. These are Hofmüller plots showing the radial profile as a function of time. So increasing time is just further inland. Black dashed line here is the 2 to 6 kilometer vertically averaged radius of maximum winds. And for reference, the white dashed line is the 10-meter radius of maximum winds. We see at the beginning, for every case, there's a strong concentration of Q diabatic heating around the original radius of maximum winds. But then we see an increasing outward expansion of Q and of the radius of maximum winds and the RMW. So in the wet case, there's much more Q at mid to higher, or farther from the center, I should say. It's more Q in the outer core. In the dry case, there really isn't all that much. So what happens is RMW expansion starts to occur as the storm weakens in every case. However, by about 12 hours, now the RMW is situated on the other side of the region of enhanced Q, or probably better put, the region of highly concentrated Q is now aligned within the radius of maximum winds. This is important because several studies over the past few decades have found that when you have diabatic heating, most concentrated within a more inertially stable region, such as within the radius of maximum winds, that heating is more efficient at accelerating tangential winds through a series of processes. So what happens at T equals 12 hours is that we see the radius of maximum winds really slow down. And it's at this point that we really saw the wet case start to become a little bit stronger than the other cases. Whereas in the moderate and dry cases, where there isn't as much heating within the radius of maximum winds, these just continue to weaken, and their radius maximum winds reside beyond the innermost domain by 20 hours. So essentially the take-home point here is that higher soil moisture supports slower decay rates once the radius of maximum winds expands beyond concentrated Q. Summarize this section, powerful TCs decay rapidly due to increased surface roughness and a reduction in surface enthalpy fluxes regardless of the surface attributes. There's a higher sensitivity to the surface roughness initially, but that sensitivity to soil moisture increases as TCs weaken. Roughness affects the most intense inner core winds, while the moisture shows, or the outer core wind field shows a stronger sensitivity to the moisture. And higher soil moisture leads to increased outer core convection, leading to increased diabatic heating rates and a broader wind field. So that brings us into section 3, where I'll talk about the boundary layer modification during landfall and just before landfall using these same simulations from the previous section. So the key thing, this is work that I'm currently doing. Some of this is kind of left over from that previous paper, and just the paper was getting to be a bit too long, and so we saved some of these results for later, for a later paper. So I'm talking about just how the upstream land surface affects boundary layer modification, or modifies the boundary layer, and then how that in turn affects the 10-meter surface wind field. So starting off with a little bit of background on what I mean by the boundary layer. In a hurricane, winds increase towards the surface, which is represented by these increasingly bigger circles and X's indicating flow into the page. And the interior of the flow is represented, or can be approximated as gradient wind balance. So that's just where the inward pressure gradient force is balanced by the outward centrifugal and Coriolis forces. If it weren't for friction, these winds would just keep going around and around the center of the storm. But because we have friction, this weakens the surface winds, smaller circle and smaller X here, which in turn leads to a subgradient layer, which really drives the secondary, or is a key component of the secondary circulation. This forces an inflow towards the center of the storm, bringing along higher momentum air along with it towards the center of the storm. So this layer is compensated by a supergradient layer at the top of the boundary layer before relaxing back into gradient-ish balance. Usually the boundary layer height is generally approximated by the depth of the inflow, because conceptually the boundary layer is essentially the layer closest to the surface that's most affected by frictional forces. So this figure down here is from Franklin et al. In 2003, and it shows a dropsonde composite of many, many tropical storms and hurricanes over the Atlantic. And this is just an average vertical wind profile for the boundary layer below 3 kilometers. For the inner core, we see this strong subgradient layer towards the surface, and a stronger supergradient jet near around 500 kilometers for the strongest storms. The outer vortex, the supergradient jet, isn't as strong, is a little bit higher because the boundary layer height does increase with increasing radius, so it's smallest nearest the inner core, before relaxing to gradient balance above. So it's very, we have ample observations of hurricanes over the ocean because it's safer to fly an airplane into a storm over the ocean. Over land, there's a lot of weird processes going on and a lot of turbulence that make it pretty dangerous to try to fly a plane into a landfalling hurricane. So unfortunately, we just have sparse observations over land. A lot of the observations of the TC boundary layer during landfall come from radars, or mobile radars, or different methods that have developed over the years. So I want to highlight a little bit about what's been found about the landfalling hurricane boundary layer. Powell in 1982 found that Hurricane Frederick, these are streamlines showing the inflow angle of Hurricane Frederick. He found that inflow angles increased to the right before landfall and within the offshore flow too before landfall. So just to make sure we're all on the same page, I'll be referring to the onshore flow as kind of the right of motion flow. That's flow transitioning from the ocean to the land surface. And offshore just indicates the flow transitioning from land to over the ocean. So he found increasing inflow angles before landfall. Other studies have found increased mesovortex and horizontal boundary layer roll activity near land, which again complicate the structure of the boundary layer and create headaches for trying to understand the vertical profile. Luckily, numerical modeling helps to fill in the gaps from what we miss from the lack of observations that we have, the lack of direct observations. One paper found that increasing the roughness increased surface convergence ahead of Hurricane Wilma. And other idealized studies have also found this enhanced inflow region within both the offshore flow and a little bit within the onshore flow, similar to what Powell found was observed for Hurricane Frederick. My question is, using my previous simulations, do I see these patterns arise from my moving high resolution TCs? And then, as I've mentioned a few times already, how do the changes in flow across the ocean-land interface affect the boundary layer winds? How does that modify the 10-meter wind field? So I want to go back to that first plot I showed of intensity and using the S10 max metric, delta P min, which is essentially the pressure deficit from the initial vortex, from the initial minimum pressure of the initial vortex, and then IKE on the bottom. All of these plots are normalized by the ocean only case. And additionally, values larger than 1 mean that the landfalling cases are stronger. Values less than 1 mean that the ocean case is stronger. Regardless of land type, we see that all landfalling simulations actually increase in intensity as much as 18 hours before landfall. So this is better seen in the not as volatile delta P min. We see this pretty steady increase and then compensating decrease back to where it was before landfall. We see these high fluctuations in intensity before landfall that actually follow similar frequencies. And I have some ideas of why this is occurring so far out, but nothing's been proven yet. So today we're only going to focus on what happens within 6 hours of landfall, and the differences between the rough and the smooth storms before landfall. So now here are some plots, some time snapshots of the inflow angle, averaged below 250 meters. On the top, I have the smooth moderate case. On the bottom, I have the rough moderate case. The TC is moving from right to left. Here's landfall. The right panels are showing 7 hours before landfall. The left panels are showing 2 hours after landfall. This dashed line is just a reference 100-kilometer radius around the storm center, just giving you an idea of the overall size. And these are quadrant RMWs here. So we see 7 hours before, the inflow is really maximized behind the storm and to the right. But then, interestingly enough, 4 hours before landfall, we see a huge increase in inflow, which is seemingly very sensitive to the upstream surface roughness. So for the rough case, we see this large elevated inflow region about 50 kilometers offshore, and a smaller one, but a still noticeable one, offshore of the smooth case. This region remains relatively stationary as the cyclone passes to the west and passes through it. So this kind of mirrors what was found for some of the studies I talked about a couple slides ago. So now I'm going to show contours of the 10-meter total wind speed. That's the contoured colors for the smooth cases at 6, 4, 2, and at landfall, 6, 4, and 2 hours before landfall. And then for the rough cases at the same times to the right. These black contours are just enclosing regions where the inflow speed is greater than 20 meters per second, indicating significant inflow. And we see, especially for the smooth case, that inflow is really largest to the right of the storm. But then as it passes closer to land, inflow becomes stronger offshore. Another key point here is that this maximum wind speed in meters per second actually increases closer to land, and then decreases again by landfall. Conversely, for the rough case, we see the same enhancement in the inflow within the offshore flow, but again, the inflow region is much larger, and we actually see that the maximum intensities defined by a single point in the storm remain pretty consistent throughout the 6 hours before landfall. So this indicates that enhanced inflow regions correlate with higher surface wind speeds, as we see that as the storms approach landfall, the wind speeds to the offshore, not only the maximum wind speed, but the broader wind field also remains strong. So this is suggesting that that modification to the inflow is playing an important role in enhancing the 10-meter winds. I should mention though, this is also kind of a reflection of how limiting the maximum intensity as defined by the maximum winds at a single point really is. Because over land, we see that the winds the wind swath for the smooth cases is still much greater than that over the rough case, even though the rough case is at a higher intensity technically. So it's just something to keep in mind. Looking at other metrics might give you a different perception of how strong the storm or how intense the storm actually is. So to understand really what's going on and why we see an acceleration of winds, especially within the offshore flow, I've plotted the azimuthal mean secondary circulation for the smooth, or the secondary circulation for the smooth case, top left, for the rough case in the middle here, and then the smooth minus rough on the right here. So blue just means rough is stronger, red means smooth is stronger. And on the bottom, I've plotted the same azimuthal, or the same thing, but for the tangential winds. And here's the difference in tangential winds. So clearly increasing the roughness, going from the smooth to the rough case, accelerates the secondary circulation, or the flow that goes in, up, and out, below about 4 kilometers by a pretty substantial amount. Additionally, when looking at the tangential wind field, or this change to the secondary circulation leads to a stronger tangential wind field above the boundary layer for the rough case and within the radius of maximum winds. So even though the harsher surface is decelerating the immediate surface winds, we see a much stronger outflow jet develop, or a much stronger super gradient flow develop above the boundary layer. So I'm not going to show a plot of the advection of the angular momentum. I do have one of those, but essentially what's going on here is that the stronger secondary circulation is just importing higher angular momentum air towards the core, which is accelerating the winds at within and above the radius of maximum winds. So I think this is my last slide. I'm going to show essentially the same picture. Now I'm calculating the deviation from gradient flow. So if you remember, the gradient wind balance is the inward pressure gradient force equals the outward centrifugal and Coriolis forces. So where you have subgradient flow, or blue colors, that just means there's a subgradient flow. There's probably an inflow. When you see red colors, that means the supergradient flow, outflow, or not necessarily an outflow, but a higher Coriolis and centrifugal force relative to the pressure gradient force. These fields are averaged within two onshore, or an onshore quadrant, which is this pizza slice here, and an offshore quadrant representing the offshore flow. So this is 35 degrees to 135, or sorry, 45 to 135, and then, oh man, quick maths, 275 to 320 here, or something like that. And so in the smooth case, we see this super gradient boundary layer jet develop, especially for the rough case onshore. The super gradient jet is a lot higher in the smooth case, but for the rough case, yeah, we do get this really strong jet developing. And something else really important to show here is that we see the presence of horizontal boundary layer rolls possibly, or just convective downdrafts that are advecting high momentum air down towards the surface. And so this super gradient flow isn't confined just to the top of the boundary layer where there aren't any people or buildings, because this flow can, or because this enhanced super gradient jet via the means of downdrafts and importation down towards the surface can create larger gusts at the surface. So another really important aspect to keep in mind, that the possibility for greater gusts can exist for rougher surfaces. Both are within the offshore flow, both land types exhibit strong supergradient jets, but it's just a little bit of a broader coverage for the rough case. Okay, so to summarize this or section 3, a strong inflow region develops about 50 kilometers offshore, which is amplified for increasing roughness, And this mirrors the findings of previous studies. Additionally, we see a brief acceleration of the secondary circulation during landfall, which effectively enhances the maximum wind speed at the 10-meter level. So now it's to wrap up with some next steps. I plan on continuing to investigate the modifications to the boundary layer, and essentially everything I covered in section 3, and how this impacts the intensity and size. And as well as a few other projects that I have in mind that I've been working on for a while before I graduate, hopefully sometime next spring or during the summer. So thank you all for listening. I hope I didn't go too far over time, but thank you for tuning in today.
All right, thank you, James. Big virtual round of applause for James. Woo. So now it's the Q&A section. If you would like to ask a question, you can unmute yourself and turn on your camera too. It makes it a little bit easier to understand people. If not, you can put it in the chat and I will ask the question.
Hi, James. Hello.
Hi, yeah.
Can you hear me? Yeah. This is Jun. Nice, really nice talk. I have a question. So you look at the effects of surface roughness and moisture on the intensity and structure evolution, and how much a connection between the surface layer and the boundary layer scheme. For instance, when you change the surface layer roughness, the boundary layer vertical diffusivity could also change. So that could also impact your boundary layer structure, right?
Yeah, definitely. Yeah, I want to mention I use the YSU boundary layer scheme, which is a non-local scheme. Obviously, as you know, accounting for kind of the bulk properties of the flow, and is possibly less affected by these very localized scale interactions. Maybe using the MYJ or a more local turbulent TKE-based parameterization would show these kind of larger modifications due to the moist convection occurring. That's a good question, but we did do some runs with the MYJ boundary layer scheme, and we did find just very small differences between the two. So possibly there isn't too much unintended contamination of the results.
Okay, thank you. Thanks for doing that.
Yep.
Another question is, you showed that when for the wet case, actually the sensible heat flux is larger. Can you explain a little bit, like the very interesting result?
Yeah, sure. Let me share my screen again. So you said, okay. Going back to this plot.
Yeah, it's a very interesting result.
Yeah. So in the dry case, in every case, the domain mean sensible heating is negative. There's a little bit of extra convective activity occurring for the moderate case here, which leads to a little bit of a warmer or a positive sensible heating. But yeah, essentially, sensible heating is more negative for larger moisture contents. So I don't remember your exact question. So if you don't.
The question is like, do you have any idea why this is the case? So that means either the soil temperature changed or the boundary layer or near surface layer air temperature is different, right? So it's kind of delta T,
right, yeah.
is related to the delta Q, reversely somehow.
So what's really happening is in the wet cases where you have more soil moisture, the cyclonic winds are evaporating more moisture into the air. So that allows, or that supports a higher latent heat flux, but that also leads to more evaporational cooling of the surface soil moisture. So that's what cools the surface, not only the surface, or the part of the atmosphere that is directly in contact with the soil. so that's what leads to that negative soil flux. It's that evaporation of, negative sensible heat flux. It's that evaporation of soil moisture that is the cause of that. And that actually mirrors some previous findings as well, but there aren't many, if any. Maybe that Shen et al. 2002 paper does, but I can't think of an instance where a previous paper has looked at the sensitivity of the amount of moisture present to the evaporation rates.
Okay, thank you. I think it's kind of like a coupled effects, because you change it's kind of a combination of the latent heat and central heat flux that together will impact maybe the convective activity. But this is a really interesting, complicated process.
Yeah,
Thank you.
It's very intimately coupled, so it's hard to distinguish what exactly is causing these effects. But yeah, thanks for the question.
I think.
All right, we've got time. Yep.
I'm just kind of thinking about, like, in the real world, these like roughness links and moisture contents. Like, how uniform do they tend to be? Like, do you have like large areas with really rough, you showed that plot in the beginning, or is there some like regional variation? Like the city of Miami probably is really high roughness.
Yeah, definitely.
So,
yeah, over the citywide scale, roughness varies by a lot. Just building to building, you can really change the roughness length or the roughness profile on such small scales. These numbers that I've shown here in this map are really just kind of aggregated or averaged estimates of Z naught. But there are papers. There's one paper specifically that I'm thinking of, I think Hirth et al. In 2012, that looked at how the near surface flow reacts to different roughness lengths over a city in Florida for a landfalling storm. And they found that the aggregate effect on the boundary layer is essentially just the summation of all the individual roughness lengths. So at a certain point, you can basically just approximate a region as an averaged surface roughness. So it's very rare to get extremely high roughnesses of like 1 to 2 meters on, say, a statewide scale, unless you had a state that was heavily urbanized, like maybe New York City would be that high. But you're definitely not going to see like an entire state being that high.
okay, cool. That kind of answers my question, because I was just wondering like how in practice that would translate. Yeah, thanks.
Yeah, no problem.
All right, maybe time for one more quick question. All right, if not, let's give James a round of applause again. Great job, James.
Hey, and I just want to say that for the committee members, I will send you an email right now inviting you to our committee meeting after this. So.
Sounds good. All right, thank you everybody for coming. And James, you just have the defense now.
I guess so.
Exciting.
Thanks, Anne. Thanks,
All right.
everyone.
Bye, everybody. See you Friday at 9:30.